All right. So this is from Bartel and Sherbert and Theorem 712. All right. And it says that if F belongs to this set, if F is a function that belongs to this set called R close bracket AB close bracket, basically that is the closed interval on which F is defined. And if this is a special set, this is a set of functions. This is this whole thing is a name for a set of functions that are integrable, which means that we can calculate the area of the function. If F belongs to this set, then we can calculate F's exact area under the function. The region under that function, we can calculate its exact area. And all right, so that's what that means. In other words, a function that belongs to this set will have a limit. And limit equals exact area. So this is L. Okay, so that is the first thing that this theorem says, that we are looking at functions under the region under them, and this is the region. We have an exact, we can calculate its exact area. That is, these functions have a limit. Okay, all right. Then, if this is the case, if we can integrate the region under it and figure out its area, we call that the limit of the limit is the integral. And integral is what? The sum of all the rectangles, or integral gives us the area. Okay, all right. So then if this is the case, then the value of the integral is, let's just uniquely determined. So uniquely determined as in calculated. So the integral is unique. Unique means 1. So for instance, I have this glass of, let's say I have this car, and I'm saying that when I weigh this car, it is exactly 2 tons. So I have my way of measuring the weight of this car, and I find its exact weight as 2, and also its exact weight is 3 tons. Is that possible? No, therefore, it has to be one, either this or this, it can't be both. If it is the exact, approximately, we could say, oh, it's 1.5 tons. Approximately, we could say it's 2.5 tons. But when we are talking about exact values, so therefore, the integral, the L has to be just one number. Can't be 2 numbers. So that is what we have to show, is that if we can calculate the area, the area of the region under a curve, under a function f, then that area will come out to be just one number, not 2. So that is the whole deal. All right. So So how do we do this proof? Well, we'll have to bring in all the math. And so so I'm actually not going to write everything down. I'm just going to try this. Let's assume, so the proof is based on contradiction. And let's assume that when we calculate the area, it turns out, let's assume that there are two integrals, two exact values for the area. So we have assumed that L and L prime both satisfy the definition of satisfy the definition of integration. Oh, I can't spell integration. Let's just pretend that's the correct spelling. All right, so when does let's see, when does a function have an integral? You guys remember what's the condition? There are like two conditions. Number one, so we're thinking about the rectangles under the curve. So the rectangles, so the first condition is this. So these are the conditions for L to exist, as in for the integral to exist, for the area to exist. The conditions are we need to have a partition, perhaps tagged partition. So we need to have a partition. So number one, and then the width, the width of the widest width or the longest width of the rectangle. How was I saying it last time? Has to be so the largest width of the base of the rectangle, its length. So the length of the widest base of a rectangle better be less than this thing here, delta. So this condition has to be there. If this condition is there, and the second condition is where, so this is the exact sum. This will exist. The exact sum will exist, as in the integral will exist. Integral exists if the region under the curve f has been partitioned into rectangles, and the limit exists, the integral exists if the difference of the integral and the approximate sum, which is the Riemann sum, and the Riemann sum goes like this. So this is the approximate sum, approximate area, or in other words, Riemann sum. Oh, good, Ellie, I need to talk to you too. Good. All right, is less than, yes. Sure, yeah, you can bring her. Hi, Ellie's friend. All right, so does this, Omid, were you paying any attention? Good. Does this make sense? So if this is true, this is what? This is the definition of an integrable function. Okay. If the function belongs to this set, this could have been named, let's say, A even. So this is a set that contains all the functions that we can, and the region under them, we can calculate the areas. If this function belongs to that, then we can say this about the function, that below the function, the region, if divided up into rectangles, partition into rectangles, and then we add up the areas of the rectangles, because the area for anything, we can calculate areas of rectangles, but not curvy things. But calculus allows us to do that. Then the approximate sum, Riemann sum, and the difference between the approximate sum, approximate area, and the exact area, or the integral better be less than another small positive number right here. And then this condition. Okay, so that means if we assume that there are two limits, two integrals, two exact sums, as in 2-ton car and a 3-ton car, then we can write two of these for each case. Okay, so I'm going to delete this. All right, so what do we do with this? We need what? We need, we're going to say, if this is true, then there exists, if this is true, this is the given. So we're going to go with epsilon first. So there is an epsilon. If there was just one limit or one integral, there would be one L, but epsilon would be right there. Okay, so we have an epsilon, and L1 and L2 satisfy the definition I just wrote. So for that, for one limit, we need one partition. For the second limit, we need a second partition. So I'm going to say that then if this is true, then there exists. So how many of the deltas do we need now? Delta goes with the, oh, cool, you're here too. Okay, so talk to me after class, don't disappear. Yeah, all right, very good. All right. Umid, are you still following? Where are you lost? Why didn't you speak up? While you are wondering what to say, are you completely lost? Chris, what about you? You're doing good? Okay. Umid, where did I lose you? Okay, all right. I know where I lost you. So this is the diagram. Here is our function f, and we need to find the area under this given a closed interval beneath the f, right? So let's say this is our closed interval. What this does is it creates a vertical line going up and vertical line going down. Now, this is the area we need to calculate the area of, right? So what's the problem? We have two sides that are straight lines. The third one isn't. We know how to calculate areas of rectangle. Height times width. But here, what about this guy? The height is changing. Okay, so when we say that this whole thing, we say that it has a limit. This function has an integral. We can calculate the value of the area under it. We are saying is that we can actually stick in rectangles. So let's say, so how do we do that? We stick, let's say we stick this guy here. Okay, all right. So we stick the rectangles, and then I'm redoing this whole thing I've been talking about for 3 weeks. For me, thanks to you. So this is the height, this is the width. Okay, so now I'm going to continue. We have the picture there. We have noise. Okay. Then there exists. Who is this? Please sit down. You're a guest. They're having, I'm having emotional issues. They're having emotional issues. It's a beautiful, nice day today, by the way, folks. All right. So then if we have this, then there exists this fella, and because we are saying that let's pretend this area. What number do we want to give this area? 20. If this is the exact area of this, including all of this, can we also say that it has the area of 25? But this is for the people who just walked in. You know how my weight is exactly? It's 200 and 230. It is, I have measured myself exact, right? I could say that I'm between, sometimes I'm 215 and sometimes I'm 230, approximately. But my exact weight is 190, which it isn't, but let's just pretend. So the exact weight would be 190, but the approximations would be around that number. Okay. So what's going on here is when I say that the area under the curve is 20 exactly and 25, I am talking nonsense. Because what the theorem is saying is the area, the exact area, which is the word integral means, has to be just unique, just one, not two, not three. And in order to prove that, we assume the opposite because this is a proof by contradiction. So, and then I showed you guys the definition already. So we have to apply the definition of an integral that exists for a function, area under the function, and we have to write that out. So if epsilon is there, then this epsilon will, remember I wrote just epsilon, we'll just divide it in two because we need two numbers now. So we're going to do it for the single quote. L first, and then we'll do the double quote. So then, so I will just write this. So for L, the area we think, the exact area for this, if this exists, we should write a couple of things. We should write this. And let's call this partition 1. And it should be less than our number here. And it depends on the existence of epsilon. And then what's the second thing? Umid, no, Grace, Umid has moved on. I need to put what here? The Riemann sum? Yes, the exact area, yeah, or the limit, right? Or the integral. So Riemann sum is f, and then here I'm going to put here's the function, the same function, and the partition. This P1 represents how I've partitioned this thing into rectangles. So I'm going to put, and it's tagged, and I don't have time to go over that because I've already gone over that before. And this represents what? This is the mesh, the norm of the partition, which means that it is this length right here. This thing here is the length of this thing. So we take the rectangle with the widest base, and that length better be very small, or better be less than this thing, and then this thing has to have L prime, and then this is less than. So we divide it by 2. If we just had 1, then we would be just using that. Okay. This is all very complicated if you don't remember the previous 3 weeks, and also the definition of limits of function. And for L2, if L2 exists, then it needs to have a separate partition, same curve, different partition, and it needs to be less, then it needs its own delta, and okay. All right, now I'm gonna make pictures for both of these lines here. And I was supposed to go over the poem. Maybe I should have done that, but there was nobody here first. So I'm like, let's just do the math. And you guys showed up, we could have done the poetry. All right, now what happens here? How do we represent this guy? So let's see. I'm gonna do right here. So I'm trying to represent, hmm, I can't do math on one whiteboard. That is the problem. Okay, I'm gonna just write this here. Delete this, and okay, for this is the picture for L1. So this guy here is, so we partitioned it, let's say with 3 of these, and that if we add up the areas of these rectangles gives us an approximate area of the region under the curve. It's approximate because what is missing? It's not exact, right? So this picture represents this little bit of math. L prime. What is L prime? And so I'm going to put minus here. And L prime is all the area. So this is the exact actual value, right? Okay. But in fact, and it's supposed to be, and so this thing is L prime. And if we take the difference of the approximate area and the exact area under the curve, that should be less than epsilon divided by 2. Okay, so that's L1. Let's do L2. So we're doing this guy here. And the picture goes, we're going to draw this first. This seems, how fine is this partition? Not really, right? It's only just 3 rectangles. Let's make a finer partition. How do you make the finer partition? By making the length of the base smaller than that. So the largest length of width of the base is this one, and it is still less than delta. And now I'm going to draw a picture here, so which will represent this guy. I've got skinny ones here. And as you can see, the error here is smaller. So this is a finer partition. This Riemann sum gives us a better approximation of the area under the curve than this Riemann sum, because this partition, the second partition, is better than the first partition. It has more rectangles, so it captures more area under the curve. And if we add the areas of individual rectangles, we get a better approximate sum, okay, of the area under the curve. And then we do the exact integral right here is less than epsilon divided by 2. Because we assume that this function has 2 exact areas, which is impossible. And actually, I need the picture here, sorry. And then this same picture goes here. And this would be L double prime. Okay, and I think we could do one more thing, and I'm not going to do the whole thing because nobody's here, or a lot of people are not here. Well, oh, and we can do some poetry as well. All right. What's the next step? What we want to do is we want to get to a place where we can compare, where we can do this basically. We can say that if we took these two exact, sorry, when is when is L prime and L2? When are these two going to be different? If the if L prime is 2 and this is 3, these two guys are going to be different if the difference between them is positive, right? So in other words, if we did this thing should be greater than 0. And so we need to be able to compare them. How do we compare uh, two different integrals when the partitions are actually different? We need this same situation, but identical partition. So what we do is we choose the finer partition by choosing the smaller norm. So this is going to be the better choice, right? Once we choose this guy, we assign that, and then we can compare them. Okay. So Chris is understanding. That's good. Umid's moved on, and I think I'll just keep going. It looks terrible, the board, as usual, like one board. Okay, so the next step is, so I'll leave these guys here. So we got two of these and we need one of them, right? So how do we do that? We're going to say let just one delta equal the minimum, and we're going to pass in, we're going to give the minimum function as a set that contains this guy and this guy. So I'm going to put that here. What is this delta going to be equal to? Grace, I need you again. Which delta is smaller? The length is smaller. Or our guest, because you've been paying attention. Very good, because the picture had more rectangles, which means that the width had to be smaller. Right? So, yeah, very good. So, versus for this, it looked like this, right? So, the one with the widest base would have to, so this number had to be bigger than this in order for this number to be smaller. So this can be bigger, this has to be bigger, and this can be much smaller for this to be still true, this whole thing. So this width is so small, we can make our delta smaller, and this will be still true. This width is much bigger. If our delta was the same as this size, this would not be true anymore. Yes? Okay, therefore, we get this. So we are halfway there. What's the other thing we need to do? We need to choose one of the partitions. Which one should we choose so we can compare L, because L1 and L2 exist and they're different numbers. So folks, so we need an identical partition. So if this is the case, then we will choose, let's see, and then we'll choose let P tag partition in fact be equal to, but we don't say that, we're going to say it's going to be this one, the finer. This is an actual jargon from math. This is a finer partition while compared to this guy here. Okay, so we're going to, just like we gave, we came up with one delta, we're going to use one partition. If you remember earlier, partition one, partition two, we're going to choose one of them. We're going to choose the finer one and just call it P. All right, and then we get, and then our mesh is going to be less than epsilon. Okay, and now we can do what? We can rewrite these two things again. So I'm going to write them right here. Okay, I am getting it, but I'm going to repeat this on Monday, by the way. You're welcome to come. Okay, so I'm going to rewrite these guys. So now I just have one. I have one of those and one of those. So I need to rewrite these two guys, right? So I'm rewriting this one. The function remains the same damn function. The partition that comes with that function is going to be this one, the finer one. So the partition is going to look like that, which means this is our symbol for the partition now. It doesn't have 1 or 2 because we chose the finer one. Just like over here, we chose the smaller number to get to represent that. With this partition comes with a smaller norm. The length is going to be smaller for the rectangle with the wider space compared to this one. So we have this minus, and this will be now less than epsilon divided by 2. We're still doing that. And then here, is this still nonsense? Now what we have is the approximate areas are the same. The exact areas are still different. And we are saying that both of these conditions are true. And if they are true, we're assuming they are true because we assume the opposite of what the theorem said. Therefore, we can now compare and if I had more board, I would write, what do we need at the end of this damn thing? Right, let's see. Because this is still assumed to be true, now we can compare these two guys. I know. Remember, I spent 3 weeks on all of this. So now we want to basically come up with one of these things rather than two, which will show us that the limit was just one single L. With the single L, this should be just epsilon, not epsilon divided by 2. Okay, so because a function that is integrable, that has a Riemann sum, that has an integral, will have only one limit, one exact sum, and that sum better be less, the difference of that sum, exact sum, and the approximate sum better be less than epsilon. So we need to get there. Right now we have this situation. This should equal what? And at this point, we have to apply 2 different things. There's something called, so the absolute value of A plus B is less than or equal to, so this is called the triangle inequality. And we want to get somewhere. Right now, what are these numbers? We don't know these numbers. We just we are told they might exist. But what we do know is we know what what this sum equals. This whole thing is less than this actual number. It's a real number. This difference is actually a real number right there. We don't know what these numbers are, but we could bring these guys in. So I'm going to replace this because this is for right, and this is, so I'm going to replace this guy with this. Plus, am I messing up here? Oh, sorry. So what I have here is L prime, and I'm going to take one of these guys and add it in. So I had the integral, the exact sum, and I added the approximate sum into this thing, and I subtracted the approximate sum, which is what this thing represents. And so these two guys. Okay, what have I done? Are these two sides equal to each other? Chris? Chris. And there, because all I've done is I've added something to this difference and subtracted it. So these cancel out. So this equality still holds. Next step, I'm going to apply the triangle inequality, which says that, in fact, how did I do that? We have to move things around. Okay, so that will work. I just need to. Okay, I subtract first, sorry, and then add. That will be easier. Thank God. Because remember, we've got a plus here. The order doesn't matter, right? So now, what do I do? The next step is I want to make this thing look like that. So I'm applying the triangle inequality. So RA is actually, this whole thing is RA, and this whole thing here is RB. So our next step will be that this whole sum is less than or equal to is RGP's friend with me on this? No? Okay. If this whole difference is A, and we take the A and put two absolute value signs around it, we took this whole thing and put two absolute value signs around it. Then we took the second, this difference here, and put absolute value signs around it. We took the B. If this is our B, we took the absolute value sign. So we went from having only one pair of absolute value signs to having, we had something in one absolute value signs. Now we have two things in absolute value signs, right? And so it mimics that, okay? And we didn't change anything because what we put in, we subtracted. And now, at this point, we can get a number. What's the number here? So we just replace this thing with, and I want to make sure, less than, not less than and equal to. This is less than and equal to. But when we replace that, we are saying that this sum, this absolute value thing, plus this absolute value thing, so we're going to replace this thing with epsilon plus 2, epsilon divided by 2, and epsilon divided by 2. If you add these two things, they're going to be less than these two things. because each one of these are less than that. We can't keep the equal to sign. And then this whole thing is actually equal to epsilon. So then what you get is, what you have here is that the difference between these two guys is less than a very small number epsilon. So if I write it here, so this is where we are right now in the proof. Okay, so this is a positive number, and the difference between the two exact should be identical limits. They shouldn't even exist. There should be just one, there should be one integral, one exact area under the curve is less than a very small number. And then we know it's supposed to be positive. When this situation happens, there is another theorem which says that L prime, if this is the case, then a theorem 219 says that we can also, this implies if this is true, which it is, we got to this stage, then in fact what it's saying is that L1 minus L2 is actually equal to 0. Not so the difference is not smaller than some very small positive number, but in fact it's actually 0. So when you're sandwiched between a very small positive number and the 0 itself, the difference is between these two guys is actually equal to 0. What does this imply? And what did we assume? That there did exist two. By the end of this, we are showing that the actual areas are identical. There are no two areas, the areas are same. That is, if a function has an integral, if a function whose area we can calculate, area under the curve, we can calculate, that area will turn out to be just one number, not two different numbers. And we got there. So this is an application of theorem 219, which we did way back in the day. All right. RGB, you're confusing me with your haircut. Like, where is my RGB? You also have changed your design and values. Okay, good, good, good. Okay. At least your friends are the same. Okay. All right. I'll go over this on Monday. What time is it? I'm calling it a close. I'm going to talk to you quickly. You come outside, secret. You guys are, Umid, get the fuck out of here. Chris, I'll see you Monday. And no class on Friday. So, yeah, it doesn't matter. Come, RGB, quickly. Okay. So, the deal is, because of your attendance, if you keep coming again, I'm going to give you an A minus. If you turn in a couple of things, just write on the poems, I'll give you an A. So that's the deal. So it's up to you. Just random sentence. Do not call me crazy. So that's the deal. That's the deal, RGB. Because your attendance was very good.
That's fine.
Because you won't turn it in without the debit.
It feels like I don't need to. It's not.
Okay. All right, then.
It's okay.
Okay, so if you don't turn anything in, you get an A. Okay, but come at least 2 more times during the semester. But if you do turn it in before the break.
Okay.
Turn in 2 things, barely few sentences each. Just write on the poem, okay? Whatever you can do. So you want your deadline to be by this one, this weekend or the next one? But that's before the break. Yeah, you want, let's do Wednesday, next week, Wednesday. Okay? And if you don't, then you know what the deal is, right? You're okay with that deal? Okay, now you come. Your case is easier. Yeah. So you turn in the first one. You can turn in the second one if you. And you can. and just write on the poem if the math is too much. Also, at this point, if you just keep coming and don't turn in anything, I'll still give you an A. That's the deal. But if you turn in,
No, I'll turn it in. I can turn it in either today.
okay, all right, because I just need 2 things out of the 3 from you. Okay, cool, cool. And just come in a couple of times. Yeah. No problem. I gave her a better deal than I gave you.
Oh.
Sorry. All right, Chris, I'll see you later. Mhm.
I was so excited to bring her to this class.
Oh,
Yeah.
so usually it's more fun today. I was stressed out because this thing is very stressful.